All right, Bismillahirrahmanirrahim. Assalamualaikum and very good evening to everyone. Thank you for joining the class tonight. So this is another replacement class. Tomorrow we will have face-to-face class and also quiz 3. Saya dah bagi tahu dalam group. So tonight we will continue the lesson about impulse and momentum. So hopefully tonight's class will be maybe less than 45 minutes, little bit more than 30 minutes. Hopefully kita boleh habiskan awal lah. Okay, so in the previous class, we have discussed about impulse and momentum. So you should understand by now that impulse is force multiplied with time for linear, and for rotational, moment multiplied with time. So that is impulse. Basically, the unit for impulse is Newton second for linear, and for rotational is going to be Newton meter second. And then momentum is m times v for linear, mass times the velocity, and for rotational is going to be mass moment of inertia, ig, multiplied with angular velocity omega. So this is the variable or the parameters that you need to understand for impulse and momentum, and it is very similar to work and energy. So in the work and energy, we have the principle of work and energy, which is T1 plus total U equals to T2, initial kinetic energy, plus total work done equals to final kinetic energy. For impulse and momentum, we have similar principle, which is called the principle of impulse and momentum, which is given by this: initial momentum plus the total impulse is equal to the final momentum. So this is the principle of impulse and momentum. And the principle of impulse and momentum is divided into three equations, right? So the first two equations are for linear, principle of linear impulse and momentum, where we write the equation in x-axis and also in y-axis. And for rotation, we have another equation, equation number 3, which is ig omega 1 plus mg dt, the impulse, is equal to ig omega 2. Okay, so basically what we have here is this side is the initial momentum, right? Initial momentum. And here we have the total impulse. And at the back, we have the final momentum. Okay, very similar to the work, the principle of work and energy lah. Okay, so for today's class, we will look at another what do you call concept, where we still look at the principle of impulse and momentum. And in the case where the middle component here, the middle component, which is the impulse, okay, this is the impulse, the total impulse lah. Total impulse is equal to, or approximately equal to 0. Okay, when the total impulse equals to 0, previously we have, this is initial momentum. Okay, initial momentum. This is the total impulse. And at the back, we have the final momentum. So in the case where total impulse is almost 0, how is the total impulse becomes almost 0? For example, when time t is very small, very small. Time t is very small. Example, let's take t is equal to 0.0001 second, for example. Very, very small. When time t is very small, regardless of whatever force you have, whatever moment you have, multiplied with 0.0001, the time, then you have something very close to zero, very small value. So what happened when the total impulse equals to zero? This equation, the middle part is gone. The middle part is gone. Okay, middle part is gone. So what happened to the equation of principle of impulse and momentum? So this will become um, mvx1 is equal to mvx2. Okay, because the middle part is gone. The middle part is gone. So what you have is only initial momentum equals final momentum. So you also have mvy1 equal to mvy2. And for rotation, we have ig omega 1 is equal to ig omega 2, right? So what we have here is initial momentum. Initial momentum is equal to final momentum. Initial momentum equal to final momentum. So what is this called? When you have something like this, momentum yang awal sama dengan momentum yang akhir. So this is known as the conservation of momentum. Conservation of momentum, right? When is the conservation of momentum happens is, for example, when the time t is very small. Okay, when time t is very small, right? Also, when you have force that, when you have non-impulsive force, okay, for example, the force at the pin connection, let's say point O, you have rotation motion, force at point O is non-impulsive. So this is the reason why we have the conservation of momentum lah. So you can notice that from the previous equations that we have, principle of impulse and momentum, we have three separate item: initial momentum, total impulse, and final momentum. Now the total impulse equal to zero. What you have now is initial momentum is equal to the final momentum. So this is called the conservation of momentum. Okay, so to better understand this, let's look at an example question, right? So when you read the question here you can see a rod, a slender rod, okay, 5 kg slender rod is at rest, okay, and suddenly there is a bullet. So the bullet is fired to the slender rod at an angle of 30 degrees, okay, and what we want to determine is, first is the angular velocity. Let's highlight. First we want is the angular velocity of the rod, okay, angular velocity of the rod just after the bullet becomes embedded in it. So what we want is, if we can write here, we want the omega 2 lah, omega 2 of the rod, okay, omega 2 of the rod. Omega 1 is equal to 0. Okay, why? Because the slender rod is initially at rest. Okay, initially at rest. So we know that initially the rod is not moving, and when the bullet is fired to the rod, then the bullet The bullet goes inside the rod and the rod starts to swing, start to rotate. So this is what we want to know. What is the rod? What is the angular velocity that the rod is swinging? Okay. So to answer this question, we need to draw a diagram. Okay, a diagram that is known as impulse momentum diagram. Okay, so we have impulse momentum diagram. Right. So we know that there are two situations here. One is when before the bullet is before the bullet before the bullet becomes embedded in the rod. So that is one situation lah. Okay, so let's bring this a little bit here. Okay, so we have the rod here. Let's say something like this. This is where point O is. Okay, the fixed point, right? So this is point O. Okay. Now, before the bullet becomes embedded, the bullet is maybe somewhere over here lah. So let's say this is the bullet. Okay, the bullet is somewhere here. Has not touched the rod yet. Okay, so we can draw the line here. Okay, and the rod is fired at an angle, so this is about 30 degrees lah. Wait, let me something like that. So we have this is about 30 degrees angle. All right. The rod is not moving, but the bullet is moving. So what is the momentum of the bullet? How do you write the momentum of the bullet? The rod is at rest. The rod is not moving. So the rod has no momentum. Remember, what is the definition of momentum again? Momentum is the mass multiplied with the velocity for linear motion. For rotation motion, the mass moment of inertia, Ig, multiplied with omega. So the rod is rotation. The rod is a rotating object, but the bullet is a linear motion object. So for the bullet, we can write that the what do you call the initial momentum of the bullet is mb. Let's write the mass of the bullet mb times vb1. That is the momentum of the bullet lah. Okay, so this is initial momentum. Initial momentum. Initial momentum. All right. So the rod does not have any momentum because it is at rest. The bullet has momentum. How to calculate the momentum of the bullet? Mass of the bullet times the velocity of the bullet. What is the mass of the bullet? The mass of the bullet is given here, 4 grams. That is the mass of the bullet, mb. What is the velocity of the bullet? Initial velocity, VB1, is 400 meter per second. So we have this mb VB1, we can calculate. Okay. Now, the next object or the next, let me copy this. The next diagram that we need to draw is what happens during impulse. Okay. Let's focus this as principle of impulse and momentum lah. Before we go to the conservation of momentum, let's focus for the principle of impulse and momentum. So we have initial momentum, we have total impulse, and we have final momentum. So we need to draw the diagram of these three parameter, these three items. Okay. So let's go to the impulse. Okay, impulse. So we go back to the definition. What is impulse? Impulse is force multiplied with the time. So we need to list down all the forces acting on this object lah, on the rod and the bullet. So now impulse is when the bullet has become embedded in it. So the bullet is now inside the rod. Okay, the bullet now inside the rod. So first we have the mass of the bullet. So we can draw pointing down like this. This is MB, the mass of the bullet, times G. Okay, MBG, the weight of the bullet. And then we have the weight of the rod. So this is MR times G, mass of the rod times G. Okay, MRG. We also have the reaction force at point O. So we can have here O. This is a rotation motion. So this will be ON, normal axis. And this side will be OT, tangential axis. Okay. All right. Okay. So we know that impulse is force times time. But if you read the question here, there is no time mentioned. Why? Because the impact of the bullet and the rod is very short, because the bullet travels very fast. Once it has come inside the rod, the time taken maybe is a few milliseconds, for example. So the time is very, very short. So because of the very short time, T is very, very small. T is approaching 0. So the impulse is equal to 0 lah. No impulse. No impulse. Okay, so now the next diagram that we need to draw is what happened after the motion, after the impact lah. I mean is after the impact. Okay, so we have the pin connection here at point O. Okay. Okay, so now the bullet is already inside. Okay, the bullet is here. All right, so what happens when the so initial momentum is basically motion number 1. Now motion number 2 after impact. Okay, this is the final momentum lah. Final momentum. Okay, so when the bullet is inside, what is going to happen? So the rod now, let's say this is point G, the center of gravity of the rod. So the rod will travel to the right. Okay, the rod will travel to the right. So when the rod travels to the right, it has momentum. This is linear motion. Let's focus on point G first. Linear motion of the rod, this is MR times VR2. V rod V rod 2 lah, VR2. And then we also have the bullet. Bullet will also travel to the right. So the bullet also has momentum, MB times VB2. Okay, MB VB2. All right. And the rod itself will rotate. So we will also have a rotation motion like this. Okay, so the rotation, impulse for rotation is IG of the rod lah, IG times omega 2. Okay, so if you look here, this is the parameter that we want to find, omega, which is omega. Okay, so by drawing this impulse momentum diagram, we can identify what are the equations ataupun the function that we have, the momentum that we have, and what is the parameter that we want to calculate, which is now omega 2 lah. Okay, so we can now write down the equation uh, to calculate this, which is we have a few momentum here. So we need to write in using the symbol H, which is used to to indicate angular momentum. In the previous class, I have shown that angular momentum is indicated by symbol H. So when people write H, it means that this is Ig omega. So for linear momentum, we use the symbol of L. Okay. So in this case, we will write down the equation total H O1 is equal to the total HO2. Okay, so this is the equation of conservation of momentum lah. Okay, HO. Why HO? Because kita calculate pada point O at the center of rotation. Okay, this is a rotating object, so the object rotates at point O, so that's why we calculate HO. Okay, so HO1. Okay, let's focus on total of HO1. What is HO? HO is the angular momentum. So if you look here, position number 1, initial momentum, we have MBVB1. MBVB1. So MBVB1, the direction, it is a linear motion lah. It is a linear motion. So we need to I will zoom in here. Okay, we will focus on the initial momentum first. So what we want is we want to resolve this into the tangential axis. So this will be MB VB. This will be MB VB1 cos 30 degrees. Okay, and then we also have for the normal axis. Now this one is MB VB1 sine 30 degrees. Sine 30 degrees. Okay, so basically we need to resolve this lah. This momentum here. This is the original momentum punya arrow, like this. Okay, the original momentum punya arrow is at an angle of 30 degrees. So we need to resolve. One is in tangential axis, the other one is in normal axis. Okay, so when we calculate the angular momentum about point O, now let's zoom in again. Point O is here. So about point O, the momentum that has moment about point O is this one lah. To go here, this will rotate in anti-clockwise direction. But this one has no momentum lah about O. So this one has no momentum about point O. So let's put a cross here. This one does not have momentum about point O. Only MBVB1 cos 30 degrees has momentum about point O. But this is not yet a momentum, an angular momentum. This is not yet an angular momentum. This is momentum in tangential or in x-axis lah. If we take horizontal as x-axis, and this one is in y-axis. So to make this a moment, an angular momentum, we need to multiply with this distance. Okay, this distance to daripada O, from point O to the the moment in x-axis ni lah, the moment in tangential or x-axis. So the distance, if we look here, is 0.75 lah. The distance is 0.75. Okay, based on the figure that we have. So HO1 is basically MB VB1 times cos 30 degrees times the distance 0.75. So daripada moment that you have, daripada linear moment, MB/VB is a linear moment, linear momentum. To make it angular momentum, you need to multiply, seolah-olah kita calculate moment. Okay, momentum, linear momentum, to convert into angular momentum, we need to multiply with the distance. Okay, kenapa kita calculate angular momentum? Because now we are using the equation for conservation of angular momentum. Okay, let's write it here. This is the conservation of angular momentum lah. Conservation of angular momentum. Angular momentum. Right? Kenapa dia angular momentum? Because this motion involves rotation. The rod is rotating. That's why it is angular momentum. And the parameter that you want to calculate is omega 2, which is the angular velocity lah. Okay. So HO1 is basically this MB/VB1 multiplied with cos 30 degrees multiplied with 0.75. So MB is mass of the bullet, is given here 4 grams. So convert that into kg. So it becomes 0.004 MB. Okay, 4 gram divided by 1000. VB1, you have 400 meter per second. So VB1 is 400. You substitute the value of 400. So now you have 0.004 times 400 times cos 30 degrees times 0.75. So you will get HO1 is equal to 1.0392. This is the value of HO1. Okay. So bila kita dah ada HO1, the next step is to find what is HO2. Nanti kita akan combine sahajalah, because the conservation of angular momentum punya equation is the combination of this. HO1 is equal to HO2. So first kita cari what is HO1. So you have already calculated. HO1 is 1.0392. Now let's go to HO2. Okay. So now I will write here. Okay. Now total of HO2 is equal to, okay, now HO2, we will focus on the graph of number 2, on the diagram of number 2, which is the final momentum. So now from here, you will see that we have IG omega 2, we have MR VR2, and we have MB VB2. All these three must be in the equation. Okay. IG omega 2 is already an angular momentum. So just write in IG omega 2. Okay, IG times omega 2. Settle. Okay, IG omega 2. Okay, now we look at MR VR2. MR VR2. Okay, this is again a linear moment. So to make it angular, you have to multiply with the distance. So what is the distance? It is the distance here from O to G. Okay, for the first one, O to G. So what is the distance from O to G? Okay, now G is, if you zoom in, G is somewhere here in the middle. Okay, the total length is 1 meter, 0.75 plus 0.25 is 1 meter. So O to G, the distance should be, the distance should be 0.5 meters. So that is the distance So you put in here 0.5 meter. There, the distance. Okay, so for HO2, Ig omega 2 dah settle. Now we have to plus dengan MR times VR2 times 0.5, which is the distance lah, 0.5. Okay. Next is MbVB2. So this is another plus. So basically kita ambil semua rotation direction in anti-clockwise lah. Anti-clockwise rotation as positive for HO2 and also for HO1. HO1 pun we do the same. So basically we take angular anti-clockwise direction as positive. Okay, remember for angular motion, we need to define the direction. Okay, so coming back to this, MRVR2 times 0.5 dah settle. So for MBVB2, the distance will be the same like this one lah, 0.75. So now tadi kita pecahkan dua. Now when the bullet has been embedded in the rod, it doesn't have the angle anymore. Dia akan move together with the rod. So now we have here MB times VB2 times the distance 0.75. All right. Okay. There are a few things that we don't know here. Okay, the first one is omega 2. Yang ini kita nak cari. Omega 2 is the one that we want to find. Next thing yang kita tak tahu adalah IG. IG kita tak tahu, tapi kita boleh calculate. So let's do that first. Okay, so IG is, this is a slender rod, so 1/12 ml square. Okay, ml square, which is 1/12. 1/12 m is 5 kg. M is 5 kg and L is 1 meter square. So you will get IG is equal to 0.4167 kg meter square. Okay, itu adalah kita punya IG. Okay, next thing that we don't know is VR2 and also VB2. Yang ini kita tak tahu. Okay, but yang ini sebenarnya we can find using equation for rotation. This is a rotation punya problem, and we learn early in the semester that for rotation, okay, we have the equation V equals to omega times R. So all this V we can convert into omega times R. Okay, so this one VR2, we know R is 0.5. So this will be omega times R. This will be 0.5 omega 2. Okay, VB pula, we know that the distance R is 0.75. So VB2 will be 0.75 omega 2. Okay, omega dia akan sama saja. Omega is basically the omega of the rod. So dia tak ada omega of the bullet. No, because the bullet, the center of gravity of the rod, the whole rod is rotating together with the rod. So dia hanya ada satu omega sahaja. Okay, so now daripada sebelum ni kita ada 1 sahaja omega 2 kat depan ni. Now we have multiple omega 2. Okay, so yang the rest ni semua kita ada value. So IG tadi kita dah calculate. Let's focus on this equation. IG kita dah calculate. So this will be 0.4167. Omega 2 is unknown. MR is mass of the rod. So this will be 5 kg. Okay, mass of the rod. Mass of the bullet is very, very small, 0.004. Okay, and then we have 0.75 omega 2 times 0.75. Okay, so end up we will get HO2. HO2 will be equal to bila kita campur-campur semua ni lah, 0.4167 omega 2, 5 times 0.5 is 0.25 omega 2, or ada multiply dengan 0.5 lagi, and then 0.004 times 0.75 times 0.75, you will get 1.6689 omega 2. Okay, this is the HO2. Okay, this is HO2. So, when we go back to the equation yang asal tadi, HO1 equals to HO2. Okay, daripada sini, kita bawa ke sini. Okay, daripada the first equation. So, what we have is then 1.0392, this is HO1, is equal to 1.6689 omega 2. Okay, so from here, we can get the value of omega 2. Okay, we can get the value of omega 2. All right, I will write here. So the value of omega 2 will be 1.0392 divided by 1.6689. So you will get omega 2 is equal to 0.6227, 0.6227, and the unit is radian per second. Okay, so this will be this will be the final answer lah. Omega 2 is 0.6227 radian per second. So this is the step to solve the problem that involve conservation of angular momentum lah, sebagai contoh ini. Okay, so do you have any question on this? So saya repeat, the first step is to draw the impulse momentum diagram so that kita akan lebih jelas in the first stage what is happening. So in the first stage, the rod is not moving. The rod is static. The one that is moving is the bullet. The bullet is from here coming closer to the rod. This is what is happening initially, step number 1. Step number 2 is optional lah, because bila you baca soalan ni and you do not see any time given, so we know that the time is very, very short. So basically the impulse ni tak ada lah. The impulse ni tak ada. So if you can draw, but also if you do not want to draw, it's okay. What we want to know is the list of initial momentum, apa momentum awal yang ada, and what is the final momentum yang ada. Okay, remember momentum is mass times velocity and mass moment of inertia Ig times omega, angular velocity. So at position number 2, you have 3 momentum. Okay, Ig omega, Mr Vr2, and also Mb Vb2. Okay, so once you have drawn this, then you go to the equation for conservation of momentum. Kenapa kita tulis HO1 and HO2? Because dia ada multiple momentum. Untuk initial momentum, you only have one. And this one, you have to resolve kepada components because there is an angle here. Okay, kalau tak ada angle, tak perlulah. Kalau bullet tu, let's say, fired straight from the left hand side sampai sini, so tak perlu resolve lah. Dalam case ni, because the bullet is fired in this direction. So you have to resolve into, one is in tangential axis ataupun dalam x-axis, because this is rotation, so this will be tangential lah. And normal axis will be pointing to the center of rotation. And we also have another momentum of the bullet pointing downwards. Tapi momentum yang ini tidak ada angular momentum about point O, because now the focus point is point O. Okay, and then you proceed lah to calculate what you have in initial momentum number 1, HO1, and what you have for HO2. And then finally, you combine these two together to get the value of omega 2 lah. Okay. So again, is there any question before we end the class tonight? I will continue with another example tomorrow in the class. We will start tomorrow at 8:30, and then maybe half an hour of another example question, and then we will proceed with quiz number 3 at 9 to 9:30. About 20 minutes or so, you will have the time to do the quiz, maybe 9:10 to 9:30, and then we will end the class at 9:30, a bit earlier, because tomorrow there is another class, another test tomorrow morning at 9:45, I think. So we need to finish the class at 9:30 so that the other students can come in. Okay, any question before we end the class tonight? Right, if there's no question, thank you. I will share the recording of this class for you to watch again and try to understand. Maybe I was speaking quite fast. You miss some information here and there. So you can always listen to or watch the recording again to understand and to prepare yourself for test 3 on Thursday lah. All right. So thank you again, and I will see you tomorrow at 8:30 face to face in the class. Right. Thank you. Assalamualaikum and have a good night.
Assalamualaikum, sir.
Thank you,
Waalaikumsalam.
Doktor.
Terima kasih, Doktor.
Thank you, sir.
Thank you, sir. Doktor, nak tanya,
Ya, boleh.
untuk esok quiz, energy and work done ataupun impulse and momentum?
Impulse momentum.
Oh, okay.
Oh,
Thank you,
sorry.
Doktor.
No. Quiz will be work done. Sorry.
Oh, work done and energy.
Work and energy, yes.
Okay.
Saya akan
Thank you, Doktor.
tulis dalam WhatsApp group nanti.
Thank you, sir.
Okay.
Right, welcome.
Thank you, sir.
Alright, thank you, sir.
Thank you, sir.
Thank you. Assalamualaikum.